Welcome to NPTEL online course on fractals and multifractals. So, in this lecture series, now we are discussing the fractal dimension and Hausdorff dimensions. In the last lecture, we have discussed the Hausdorff dimension and its properties, and what are the equivalent definition of Hausdorff dimension by using different covering of a set and different example we have discussed. So, in this lecture we are going to discuss the properties of Hausdorff dimension and some example, interesting example we are going to discuss. So, let me recall what is the Hausdorff dimension. For any set K in R power n, for S non-negative number, for any delta greater than 0, the S dimensional Hausdorff measure is defined as like this one. If this limit tends to 0, then it is called the S dimensional Hausdorff measure of an set K. If this limit usually exists for all the value of S, whereas it is infinity or 0, it is existing, there is a jump point where this measure get jump from infinity to 0. That measure we are calling as a, that critical point we are calling as a Hausdorff dimension, that given here. Now, based on this definition, we are going to discuss some property. Now, you can note that here we are taking the ui as a delta cover of K, where ui is a any open cover of K. Now, the value of Hs of S is unaltered. If in this equation, in the S dimensional Hausdorff measure, if you are taking delta cover by sets ui that are closed instead of open cover, if you are taking the ui as the closed cover, this value does not change, that we are going to prove. The value of Hs of F is unaltered in this equation. We consider only the delta cover by sets ui that are closed, that means closed cover. Now, let this symbol denotes H delta power S of F restricted to closed denote the infimum restricted to delta cover by closed set. We are covering F by the closed sets and find the diameters. Likewise, we can cover many sets, many collection. Among all the collection, you can take the minimum, that we are calling as this notation H delta S of F restricted to closed set, this symbol. We need to show that this restricted closed cover does not change the Hs delta of F. The S dimensional Hausdorff measure, it does not change the values when you are taking, instead of the any cover, we are taking the closed sets. If this is not changed, hence does not change on the Hs of F. If it is not changed for any arbitrary delta, then delta tends to 0, it will not change. This one we need to prove. That means Hs of F equal to limit delta tends to 0, Hs delta of F we need to prove. Now, since every closed delta cover is also a delta cover, every closed cover is also a delta cover. We therefore, from this one we can observe that Hs delta of F less than or equal to Hs delta of F restricted to the closed set, because here closed set of diameter delta we are taking. The first step we are in. This inequality we can maybe call it as this equation as 1. Now, you need to take the reverse part. This one is less than or equal to this quantity. For proving that one, let ui be any delta cover of F. Let ui be any delta cover of F. For each I, consider the closure of ui's. we observe that ui bar is closed. The closure ui is defined as ui union of limit points of ui is u closure. Therefore, we conclude that ui is a closed. If ui covers f, so ui bar, this collection still covers f. For example, if you are taking closed interval 0, 1, take deltas 1 by 2, then this set, if you are taking 0, the open set 1 by 2, 1 by 2, union 1 by 4, 3 by 4, then union 1 by 2, 1. All are different set because utmost diameter delta, diameter is delta. So, the utmost diameter is delta means this can be less than or equal to, here if we can take any interval, need not be equal interval. So, this will covers the closed interval 1, maybe here it 1 by 2 ignored, maybe you can take union of 3 by 4, 1.5, so 3 by 2, 3 by 2 we can take. This is one cover which covers this set. If you are taking the union of all the sets here, this is my u1, u2, u3, u4, then union of I equal to 1 to 4 ui covers the closed interval 0, 1. Now, take the closure of all the set. The closure of, if you are taking all the set, then it will include the end points minus 1 by 2, 1 by 2, union 1 by 4, 3 by 4, this is quarter to 3 by 4, and 1 by 2, 1, union 3 by 4, 3 by 2. If you are taking the closure of all the interval is given here, still it covers the closed interval 0, 1. And one can observe, if here in this collection we may call this as one collection capital U1. In this collection, if each set has the diameter at most delta, then this is not 3 by 4, 1 by 2 is not at most delta, maybe 3 by 2, 1 plus 1 by 4, 5 by 2 we can take, 1 plus 1 by 4, so we can take 5 by 4. So, this is 5 by 4, because if you are taking the 3 by 4 to 5 by 4, it will cross the delta length as 1 by 2. This is also 5 by 4, 3 by 4 to 5 by, that means which is equal to 1.25, which this one we can take as 0.75. So, if we are subtract this one, we will get the maximum delta is 1 by 2, it is not 3 by 2, it is 5 by 4. Now, in this mu 1, we have this set of open cover. If you are taking the closure of this ui, when you are getting, that means each sets we can take the closure, we are getting this one. If each set has the utmost diameter delta, then the closure also, just we are adding the end point, it has the diameter at most delta. Therefore, the closure preserves the diameter, that means the diameter of mu I closure equal to diameter of ui. Since by the continuity of the matrix, the supremum among all this ui, any pair of element in xi, you can take the supremum, which is equal to, you can take any pair of element in xi and find the difference, take the supremum, both are equal. So, therefore, the mu I, diameter of mu I bar is less than or equal to delta. So, mu I bar is a valid delta cover by the closed sets. We are collecting any delta cover of f and taking its closure, it gives the closed cover of F. Now use the summation diameter power S, the closure power S equals summation I equal to 1 to infinity modulus of ui power S, both are equal. Now since every delta cover ui gives a closed cover of ui closure, taking infimum gives, then this is the S dimensional Hausdorff measure definition. This restricted to the closed set which is less than or equal to mu I power S. This is taking the infimum. So this is less than or equal to this summation, because this is the one quantity, infimum is less than the all the quantity. Then this can be written as sum of mu I. Now you can take the infimum over this right hand side. This side alone one can take the infimum on delta cover, then it will becomes Hs of F of all the delta. This is the cover restricted to the closed set. This is all one. So combining this two second equation and the first equation, Hs of F containing Hs of F restricted to closed set, and here in the two Hs of delta restricted to closed set less than or equal to this set, we can conclude that this one is true. So this is true for arbitrary any delta greater than 0. Therefore take delta tends to 0, then Hs of F restricted to closed set equal to Hs of F. So if you change the cover by the closed sets, still the Hausdorff measure is same. So with respect to the closed set, S dimensional Hausdorff measure is unaltered. Now the second problem. So 0 dimensional Hausdorff measure of F equals the number of points in the set F. Now for S greater than or equal to 0 and delta greater than 0, define H delta S of F is defined like this one as per the definition. If this delta tends to 0, then this will give the S dimensional Hausdorff measure of F. If S equal to 0, if you take S equal to 0, so this power will get 0. So mu I power 0 will gives 1. So we are counting the number of, for every non-empty set it will gives the count 1. Every non-empty set it will give the number 1. So if F is finite with n point, you can keep in mind mu I, the diameter of power 0 is 1 for every non-empty set mu I, because mu I is the covering of the finite set F. Now there are two cases in F. F is finite with n points. Suppose S has the only finite number of points. Then we can find what is the upper bound and the lower bound. For any delta greater than 0, cover F by the n singleton set ui, because singleton is closed. So we can cover by the closed set, not an issue, because the measure is not unchanged with respect to the closed sets. So we can use the singleton set to cover the F, each of which has that diameter 0 which is less than or equal to delta for any delta greater than 0. Each of which has the diameter 0, which is, because if you are finding any two element in here, there is a single point only if the distance is 0. Therefore it is less than or equal to delta for any given delta greater than 0. Therefore if you are finding the H delta S, that means H delta 0 of F, this side we are taking the infimum. This is less than or equal to sum of mu I power 0, which is equal to, why we are taking I equal to 1 to n, because we have the n number of elements. So I equal to 1 to n number 1, so it will give the number n. So the upper bound is n. That means H delta 0 of F, if F is finite set which is less than or equal to n. We will try to find what is the lower bound. Since the point of F are distinct, x1, x2, xn, there is no meaning that we are taking the same element. F are distinct, they have a minimum pairwise distance. That means if you are taking any pair of element and find the distance that is greater than 0, then you can find the minimum among all the elements, that is the D minimum. Distance between all the pair we can find, among all we can find the minimum. Now choose deltas less than D minimum. Choose the deltas less than D minimum. So any set mu I in a delta cover has a diameter less than D minimum. Any set mu I in a delta cover has the diameter less than D minimum. So it can contain at most one point of F. This diameter distance between any pair of element we are taking as D minimum. Now we are choosing the deltas less than this number, delta is less than this quantity. If you are finding the mu I is a delta cover has a diameter less than D minimum, so it can contain at most one point in the F. Therefore, at least n sets are required in any delta cover. If you are choosing delta less than D minimum, at least we need the n sets to cover the in the n set need to cover F, that least at least n sets are required. Giving this one, H delta 0 of F is greater than or equal to n. So here it is less than or equal to 1, combine 1 and 2, then one can get H delta of 0 of F equal to n. This is for all the delta. If limit n tends to 0 also, limit delta tends to 0 also, this is true. If the set F is finite set, then the 0 dimensional Hausdorff measures provides the number of element in the set F. In case if F is countably infinite, it is a countably infinite set. So for any m belongs to n, choose m distinct point of F, because F is a countably infinite set. It has the form like this one, x1, x2 and so on. For any m belongs to n, choose m distinct point of F. Choose the m distinct point in the F. By the same argument as in the finite set, for sufficiently small delta, any delta cover of F requires at least m sets. Since m is arbitrary, H delta F equal to plus infinity, because for each m we have n, so it goes on, it has the n at least m element, so m is arbitrary, therefore the 0 dimensional measure of F is infinity, that means which is equal to the cardinality of the set F, which is the number of set is infinity. For any m belongs to n, we can choose m distinct point from the uncountable set F and apply the same reasoning. Hence, H 0 of F equal to plus infinity equal to F. In all the case, since mu power 0 is 1, the number of element for every non-empty set mu, the quantity H delta of F counts the minimum number of non-empty set needed in a delta cover of F. As delta tends to 0, this equals the cardinality of F. Since no single set of sufficiently small diameter can contain more than one element, therefore H delta of F equal to the cardinality of F. This is the cardinality of, that means the order of F we mentioned in the previous lecture. So which is equal to the cardinality of F. That is, the 0 dimensional Hausdorff measure is simply counting measure on F, counting measure on F, number of element, it is simply counting. So if we want to find the Hausdorff dimension of any finite set or countable set, that is equal to 0 as per the above results. Now the S dimensional Hausdorff measure is countably subadditive. So in the construction of S dimensional Hausdorff measure, we proved that if we are taking The Fi's are disjoint Borel sets. It is the countably additive. Now, if instead of the Borel set we are taking Fi as the random set, and we need to prove that the S-dimensional Hausdorff measure is a countably subadditive. So that means Hs of union of Fi less than or equal to summation Hs of Fi. For delta greater than 0, define the delta approximation as follows. Hs of F equals infimum of this summation over different covering of delta covering of F, where a delta cover means F contained in union of this mu I with diameter is less than delta for all the I. The Hausdorff measure is then Hs of S, we need to take the limit among all this one, then limit tends to 0, we will get this one, or we need to take the supremum delta greater than 0 Hs of F for all the delta greater than 0, that is equivalent. So, subadditivity of Hs of delta, let Fi be a countable collection of sets. Fi be a countable collection of sets. Fix the epsilon greater than 0 and delta greater than 0. For each I, since Hs of Fi is an infimum, there exists a delta cover mu j of Fi such that this diameter, this set's diameter less than or equal to Hs of Fi plus epsilon by 2 power I. This is true. Now, construct a cover of the union, the collection mu I j, where I and j greater than 1 is a countable delta cover of union of Fi, because the union of Fi is contained in the union of this sequence mu I comma j, where I running over 1 to infinity, j running over 1 to infinity, with all the sets diameter is at most delta. Apply the infimum. By the definition of the infimum, the Hs of union of Fi less than or equal to this quantity, double summation of mu I of S, which is less than or equal to summation Hs of Fi plus epsilon by 2I, then one can prove this one can be equal to Hs of Fi plus epsilon. Since epsilon is arbitrary, then we can get this quantity. Take the delta equal to 0, since the inequality hold for all the delta, delta greater than 0, then take delta tends to 0, one can get Hs of union of Fi equal to limit delta tends to 0 Hs of union of Fi, which is less than or equal to limit delta tends to 0 this quantity, which is less than or equal to this one. Therefore, we can say this quantity is less than or equal to this quantity. Thus, countably subadditivity of the set, one can arrive from these two last inequality, one can arrive the countably subadditivity of the Fi. So, this confirms that Hs is a countably subadditive set function. So, instead of the Borel sets, disjoint Borel sets, if you take the any random sets Fi, it satisfies this one. So, in the last lecture, while proving the Hs forms the measures, empty set has the measure 0 for all S. If E contained in S, Hs of E is less than or equal to Hs of F, we proved. Along with this property, this countably subadditivity also, we can confirm that Hs forms the measure. This measure we can call it as a S-dimensional Hausdorff measures. Now, let us discuss another example in the real lines. Let F be the set of numbers in 0, 1 whose decimal expansion do not containing the digit 5. Then the Hausdorff dimension of F, we need to prove that log 9 by log 10, that means natural logarithm of 9 over ln of 10. Let F consisting of all x belongs to 0, 1 whose decimal expansion is x equal to 0.001 D1, D2, D3 etc., where Di is any number from 0 to 9 excluding the number 5, excluding the number 5. Uses only 9 digit out of 10 because there are 9 digits only we are using. This analogous to the Cantor set construction, but in base 10 we construct F in stage by removing the number containing the digit 5. In each step we are removing the number containing the digit 5. Start with the closed interval 0, 1, one interval of length 1. Step 2, retain 9 sub intervals of length 1 by 10, remove those with 5 in first decimal place. So in step K, retains 9 power k interval, each of its length is 1 by 10 power k. So we have 9 power k intervals, each of its length is 1 by 10 power k. Now at the stage k we need nk equals 9 power k set of diameter, delta k is 1 by 10 power k to cover the set F, because each step we have this many number of sets with the diameter 1 by 10 power k. So we need 9 power k sets of diameter 1 by 10 power k to cover the set F. By box counting heuristic method 1, we can easily say the Hausdorff dimension of F is equivalent ln nk by ln delta k, limit k tends to infinity. So limit k tends to infinity ln 9k by ln 10k, which is equal to ln 9 by ln 10. So this can be alternatively we can prove by using the iterated function system. So for generating the F, we need a iterated function system of 9 mapping this Sj of x equal to k plus ai by 10, where j equal to 1 to 9, we have the 9 mapping. Each of this Si is the contraction mapping with the contraction ratio 1 by 10. Now we have the 9 contraction mapping, each of its ratio is 1 by 10. So geometrically similar mapping, that F can be written as the union of all the mappings. Therefore if you want to find the Hausdorff dimension of DH of F, which is equal to S, the S satisfying the number of mapping times 1 by 10 power S equal to 1. That S satisfying this equation is called the Hausdorff dimension of F, that means the Cantor set. So this one we can find 1 by 10 power S equal to 1 by 9. So taking the ln on both sides, then one can get S ln 1 by 10 equal to ln 1 by 9. So S can be obtained as ln 1 by 9 to 1 by 10. So which is equals ln 9 by ln 10, which is given here. So by using the method of constructing this F with the iterated function system, that means the geometrically similar mappings, there are 9 mappings with the ratio 1 by 10, we can find the Hausdorff dimension of the attractor F. This will satisfying this equation, so we can find the Hausdorff dimension. Now this result can be generalized as, let F be the set of number in closed interval 0, 1 whose base B expands and omit m specific digits, m specified digits, leaving B minus m allowed digits. Then this sequence of numbers, the IFS consisting of B minus m maps, each which contraction ratio 1 by B. So B minus m number of maps, each of its contraction ratio is 1 by b. So, the Hausdorff dimension of this attractor F satisfying this equation. So, the similar argument one can get this, the ln of 1 by b time s equal to ln of 1 by b minus m. So, the s one can get ln of 1 over b minus m over ln of 1 minus b. So, here one can get ln of b minus m over ln of b. So, now according to the base expansion, in the previous one we are in the base 10 expressions, the digit 5 is omitted. If we omitted particularly m specific digit, then leaving b minus m allowed digits, then the attractor has the fractal dimension, that means the Hausdorff dimension ln b minus m by ln b. Now, let us discuss one more example related with the Lipschitz mapping. Consider the function f from R to R defined as f of x equal to x power 2. Then the Hausdorff dimension of f equal to Hausdorff dimension of f, where f is a compact subset in R. We know that the f of x in R is not an uniform continuous, that means not Lipschitz throughout the region R, whereas it is locally Lipschitz whenever you are taking the compact sets. So, we need to show that the function f of x equal to x square preserves the Hausdorff dimension of any compact subset of f in R. That means this result state like this one, that means this x square preserves the Hausdorff dimension of any compact set f. That means if we have the real number here, so we can consider here one real set and here another set, then f is mapping from here to here. If you are taking any compact sets here, maybe in the any interval here you can take, it is a compact set, the a to b you can take, then find the image of f of a to b here, f of a to b here. Then if you are finding the Hausdorff dimension of this set, which is equal to the Hausdorff dimension of the original set, that means the under this mapping f, the Hausdorff dimension of the set is unaltered. That means the f preserves the Hausdorff dimensions, Hausdorff dimension of any compact sets. Here I am taking the closed interval a comma b. For any compact set f in R contained in R, f of x equal to x square is locally Lipschitz. When this interval it is Lipschitz. By the mean value theorem, for any x comma y belongs to f, this modulus of f of x minus f of y is less than or equal to this quantity times x minus y, where this quantity is supremum among f days of z, where c equal to supremum of z belongs to f, where here 2z, because f days of z one can get as the 2 times z. We are taking the function as x, so it is a bounded functions. Then modulus of f of x minus f of y less than or equal to c times modulus of x minus y. So, this f is a Lipschitz mapping. So, as we already proved that if f is a Lipschitz mapping, then the Hausdorff dimension of f of f is less than or equal to Hausdorff dimension of f. This is true. We can take this as first one. Now, we need to prove the reverse inequality. For proving the reverse inequality, if we consider f is a domain that does not include the origin, or by partitioning f into the pieces f intersection open interval 0 comma infinity and f intersection minus infinity to 0, this interval, the mapping f is by Lipschitz. This means there exists C1, C2 greater than 0, that the distance between fx minus fy, this one is bounded by C1 times distance between x and y and C2 times x distance between x and y. Under the bi-Lipschitz transformation, the inverse map is also a Lipschitz on f of f. So apply the Lipschitz property to the inverse gives dh of f can be written as dh of f inverse of f of f. So f inverse of f of s less than or equal to dh of ff, because f inverse is a Lipschitz. So if you find the Hausdorff dimension of Lipschitz function, this image which is less than or equal to dh of f. So this you can take as to dh of f less than or equal to dh of f of f. Therefore from 1 and 2 we arrived this result. The Hausdorff dimension of f of f equal to Hausdorff dimension of f. So here again f inverse is the Lipschitz on f of f. The same rule we are applying here. Therefore, if this quantity, the Hausdorff dimension of f inverse of this one is less than or equal to Hausdorff dimension of this set. So from 1 and 2 we can arrive this result. That means if you are taking f as a function x square on R, you can take any compact set in R, then under this mapping f, the Hausdorff dimension is same for both the set and its images under this mapping. Now let us take some fine example in R and find the Hausdorff dimension. Let take f equals 0 union n power minus 2 for n belongs to n. So this set f is precisely containing 0, start from 1, 1 by 1 power 2 is 1, comma, then 2 if you are taking 1 by 4, 1 by 9 and so on, it goes on. So that means 1 by n power 2, the sequence we can consider with the union of this number 0. So 1 by 1, 1 by 2, 1 by 3 you can take, it is 1 by 9, if you take 1 by 64 and so on. We need to claim that the Hausdorff dimension of this set f equal to 0. For any s greater than 0, we show that hs of f equal to 0. Therefore, s we will get the Hausdorff dimension we will get as 0. For any s greater than 0, we show that fs of f equal to 0. Covering each point xn over n square by an interval un with the diameter epsilon by 2 power n. So fixed delta as epsilon by 2 power n and cover 0 by an interval of diameter delta and cover 0, the element 0 by an interval of diameter epsilon. Then the sum of ui power s less than or equal to summation ui power s less than or equal to epsilon power s plus sum of this quantity epsilon time 2 power minus 1 power s. Then here one can take epsilon power s as outside, then one get 1 plus sum of 2 power minus ns. Since the series is convergence, because this is less than 1, this quantity is less than 1, then this modulus, this summation is less than or equal to cs time epsilon power s is convergence to 0 as epsilon convergence to 0. This raise the power is converges to 0. Thus hs of f equal to 0 for all s greater than 0. Hence the Hausdorff dimension of f equal to 0. Now for the same set f, let us try to find the box counting dimension of f. Let n of epsilon be the number of interval of length delta needed to cover the set F, where F is our set this one, F equal to 0 union 1 by n square, where n belongs to natural number. So, F points are xn equal to 1 by n square with the spacing. If you are finding the space between any two consecutive terms in this one, it satisfies xn minus xn plus 1 is directionally proportional to 1 by n power 3. Define n of delta by 1 by n of delta power 3, which is direction proportional to epsilon. So, one can get n of epsilon equal directionally proportional to epsilon power minus 1 by 3. So, split into two parts. One is when n is less than or equal to this one, that means spacing is greater than epsilon. If the spacing is greater than epsilon, then the number of interval directionally proportional to epsilon power minus 1 by 3. Then in the second case, n is strictly greater than n of epsilon. Here n is less than or equal to n of epsilon. If n is greater than n of epsilon, then points lie in this interval 0, in the closed interval 0, 1 by n of epsilon power 2, which is equal to, that is, which is directionally proportional to epsilon power 2 by 3, which requires, which is epsilon power 2 by 3 over epsilon. This is epsilon power minus 1 by 3. So, in both the cases, in these cases, that n of epsilon directionally proportional to epsilon power minus 1 by 3. So, in these cases also, n of number of interval required to cover this F is epsilon power minus 1 by 3. So, n of epsilon in both the cases epsilon power minus 1 by 3. Then we need to find the dimension of F by using this relation. So, one can get the box counting dimension from this relation. The box counting dimension of F is, so ln the number of boxes over the sizes, the size is 1 by 3, ln of 1 by 3 minus. So, if limiting case epsilon tends to 0, then one can get it is equal to, we will get it is equal to 1 by 3, is 1 by 3. So, the box counting dimension of F equal to 1 by 3, box counting dimension of this set F is 1 by 3, whereas if we are finding the Hausdorff dimension of the set F is 0, that we obtained here, the Hausdorff dimension is 0 and the box counting dimension is 1 by 3. Now, the question, for this set the box counting dimension is greater than the Hausdorff dimension. D of H of F is strictly less than the dB of F. The box counting dimension of this set is strictly greater than the Hausdorff dimension of F. Just to recall that in the definition of Hausdorff dimension, we are covering a set by diameter at most delta. That means we can take the closed interval at most diameter delta. Whereas in the box counting dimension, we are taking the covering of equal size of boxes. We are taking the covering in which all the balls has the same sizes. So, if you are taking the same sizes which is contains the arbitrary epsilons, this collection is a subset of this one, which is the larger collection will get. Now, in box dimension is generally easier to compute than the Hausdorff dimension, because it uses cover by sets of a fixed size. Box counting dimension use the fixed size, whereas Hausdorff dimension allows covering by a set of arbitrarily varying sizes. So, this one, if you are finding any set in R power n, if you are taking any set, find the Hausdorff dimension and find the box counting dimension. That means both are we are the box counting method, and this is the Hausdorff dimension. Both we can call box counting dimension, we can call as the fractal dimension. So Hausdorff dimension is always less than or equal to box counting dimension of f if you are f from the R power n. So it shows that in general, for any f belongs to R power n in the order n tuple with respect to the Euclidean metric, the Hausdorff dimension of f less than or equal to box counting dimension of f, because previously whatever we discussed the set, the Hausdorff dimension, box counting dimension are equals, whereas this specific state, the Hausdorff dimension and box counting dimension not equal. Moreover, the Hausdorff dimension is strictly less than the box counting dimension, and f is belongs to R power n, therefore the both the dimension are bounded between 0 and n. 0 and n. So this is the interesting relation between the Hausdorff dimension and box counting dimension. We can think about, if the sets are fractal, almost all the sets, this box counting dimension and Hausdorff dimension is same. For in the smooth sets also it is same. Now you can consider the attractor constructed by this figure. We already discussed the similar type of attractor. That means we can take the unit square in R power 2. This is subset of R power 2. We can consider the unit power in R power 2. Now this unit square is divided into 1 by 4 boxes. We can cover this one by boxes of size 1 by 4. Maybe this one. Now this one and this one and this one you can consider. Now assume that each has the equal, this is side length is 1, so this side length is 1 by 4. Now previously we constructed the Cantor dust by removing all the segments, only keeping on this 4. Only keeping on this 4, we constructed the Cantor dust. But this attractor, now keeping on all the 4 in the corner, this we are keeping, and keeping this middle part, the 4 sub squares. So this 4 sub square we are keeping. So this 4 squares has the side length 1 by 4, each of which has the side length 1 by 4, whereas this has the side length 1 by 2. So in the previous case we constructed all the squares as the same ratio, but here after the first step, this is the after first set we getting the set with the 2 different ratio. This is as the ratio 1 by 4, this is the ratio 1 by 2. Similarly, divide this one as a 4 parts like this one, then keep 1, 2, 3, 4 and this middle one. This 4 has the ratio 1 by 4 by 2, this is 1 by 4 power 2, and this we are keeping, this has the ratio 1 by 2 power 2. So this has the ratio 1 by 16, this has the ratio 1 by 8. So the same procedure apply here and here and here, we can get this 4 sets. If you applying the same procedure here, this can be divided as like this one, then we need to remove points into here, this we need to keep, 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 and this we need to keep, this one and this one, this will get this like 4. Now this is 1 by 2 times 1 by 4, whereas this one gets the 1 by 2 power 2, 1 by 4, this is 1 by 8, the ratios. So continue this process, then finally we are getting after nth stage we will get the attractor like this one. So, this is subset in R power 2. Let us try to compute the Hausdorff dimension for this figure. For this figure, the Hausdorff dimension is, so let F denote the limiting fractal shown in the figure. We use the self similarity of F to estimate its Hausdorff dimension. That means the similarity mapping applied on F, then F can be written as union of the similarity mappings Fi's. So, here we are using two different similarity mapping, one with the ratio 1 by 2, another with the ratio 1 by 4. So, one central copy of itself scaled by 1 by 2, 4 corner copies each scaled by the factor 1 by 4. So, 4 copies after the first iteration, first step, 4 copies has the length 1 by 4. Here you can see 1, 2, 3, 4 copies has the ratio 1 by 4, 1 copy has the ratio 1 by 2. Here 1 and 1 copy has the ratio 1 by 2. So, then F can be written as union of Si of F union of S5 of F, because there are 4 mappings are needed to map this one as here and this one as here, this one as here and this one as here. We need 4 mapping. One mapping is needed to map the whole set to here. So, here there are 4 mapping is needed, each of which contraction factor is 1 by 4. So, here we need only one mapping, this mapping the contraction factor is 1 by 2. Now, we know that if F is written as like the self copy of itself, finite self copy of this one, then we can write the 4 copies of the ratio 1 by 4 power S plus 1 copy of ratio 1 by 2 power S equal to 1. The solution of this equation, will gives the Hausdorff dimension of the set F, right? The Hausdorff, the self similar set with the contraction ratio Ri, the Hausdorff dimension S is satisfy this Morgan equation, summation I equal to 1 to m Ri power S equal to 1. So, if we are solving this equation, one can get the dimension is 1.36. Now, you just see the figure, this is contained in R power 2, we are using 2 difference ratio, and the dimension of this figure, that means dimension of this attractor in R power 2 is 1.36 approximately, the box counting dimension of this F, whereas we previously constructed by using the single ratio 1 by 4. There will be no this set, then again it will split like the 4 set, just you can imagine without this center part, then it has the box counting dimension as 1, here this set has the box counting dimension 1.36, because here we are using 2 different ratios, maybe compare with the previous Cantor does, this set more dense in the R power 2. Now, I just compare this result. Now, just in the previous lectures, we have shown that these 3 figures is a fractal interpolation function generated for the given data set here, this 3 data set with 3 different scalings. Both are different attractor. By seeing this image, one can conclude that all are having the different structures. You can check that in between any 2 interval, it has the different patterns. But surprisingly, all these fractals has the same fractal dimension. That means the box counting dimension is 1.42, 1.42, 1.42. Now, the question is how to classify the fractal object, 2 different fractal object by its dimension. But if you are finding the box counting dimension or Hausdorff dimension, sometimes it will gives same dimension for though the attractor is generated by the different iterated function systems. Now we need some strong measure to classify the fractals, though it have the different structures, though it have the two different structures, we need to classify by its distribution. You just keep in mind the Hausdorff dimension as well as the box counting dimension. Both the dimensions are obtained by covering the attractor or the set by the closed balls of size epsilon. Both the dimensions are covering the sets by the epsilon cover. So there is some information is missing what is inside the box. Sorry, some information is given inside the box. So this can be the lead to define what is the multifractal measure that we will discuss in the next lecture. Thank you. So one can refer these books for the more details. So thank you.